extraction part happen?
You have to generate one of the commands on your own. So I went through the spreadsheet, and this is one of the commands.
Oh, that's a test. Those are tests. Test conditions just to make sure that they were all working.
No. So you have to go through the spreadsheet, and you have to make one of the commands in hex for any of the register combinations, and then when you give it to that function, it'll print out that hex for all of the register combinations. So you have to go to the worksheet, and you have to do it once for each command. But once you do it once for each command, you give it to the function.
It just goes through and figures out what the rest of them are based on.
Yeah.
Okay, that kind of makes sense. That seems a little bit more difficult than it is, but now that I get it, I kind of understand what's going on.
So if you found the command for b minus equals a, you would give it to that function, and it would start from the top and do a minus equals a minus equals b, and it would give you all of them.
Wow, that's what the bitch shifts are for. I was so confused as to what your program was actually doing. Now I get it. Now it makes a lot more sense.
I think I have something that makes it.
No, I got it now.
Like I've had some comments in it before.
After I come back from
I
Canada.
didn't realize what exactly it was doing.
So
They'll all be graded in time. Yes, I'm lagging behind a little bit.
I understand it now.
don't know.
Yeah, so you have like the
Okay.
representation of this command using the 26 bits, and so 5
Yep,
bits
I have
over
to
from the left,
spend some
1,
time
2,
to do
3,
that.
4, 5. This corresponds to one of the registers.
Yeah, I see what you're saying. So you just
So
take
you just
those.
clear it out, add the new register that you want for the loop, and you just keep doing that for all the variants.
Cool.
And that's also why you can use any variant of the command to it, because it'll just clear this out anyway. So if you start off with b minus a, it'll still start, the loop will start from a minus equals a.
Yeah.
Because it clears this out.
It just resets it and then just populates all the possible options. That's nifty. That's one way to do it.
That's pretty much what TAC is.
All right.
That's what TAC is probably going to do with this.
So you guys can choose, what example we can use. I'm thinking about string length, as an example.
You should give us one over here and see if we can get it done in the same time you can be here. Seriously, give us one.
Okay, how about string length? Is that a good
We'll do
example?
string length?
Yeah, just regular string length or?
So do a man string length and find out what it does and see if we can get a program.
Yep, exactly.
Wait,
You
string
guys want to
length.
work on the string
Define the
program?
length of a string. Yep.
Define the length of a string.
Yeah.
Like create
Taking
our
the
own.
C program and turning it into assembly for our processors.
Oh.
What he just did in class.
Earlier, but take out some of it.
Yeah, it's a simpler version of that. Yep.
You guys want to do that?
But this one needs a count too, so in a way it's a little bit more complicated, but not by much.
Add the definition of string length to a file on the drive, so we can all start with the same code. Like same C code, I mean.
Same C code?
Same C code.
Well,
yeah.
I haven't created a C code yet because I want to look up the actual definition. I know it already, but I just want to show that to the whole class. Then we can work on the C code. Once I save the C code, you guys can just take it. Yep.
Cool. So you can we'll be back from break. Let's see.
Okay. Where you going? Okay. Okay. All right. All right. So I'm gonna start the record. The recorder has started already, so I'm just gonna get started with this process. So I'm gonna do basically the same thing as what we did in class, but this time it is applied to string length, which is another string function. Okay. Now I like string functions because they involve the use of pointers, dereferencing, compare, and stuff like that, which is basically all the stuff that I need to make sure that the processor is able to do, and all the instruction set, the opcode that we have done up to this point can also do. So in this case, we have implemented string length, which is determining the length of a null byte terminated string. Okay, it returns a non-negative number. Okay, can be a 0 if the string is null, and can basically return the number of non-null characters within the string. Yes, go ahead.
I just want to ask if you're recording.
I think it is recording. We'll double check. Double check. Recorder. Yep, it is on. And of course, the other thing we need to check, which we did a little bit earlier, is that we have enough space, and we do have enough space here. All right. So I'm going to save this document and rename it to string length, which is reflecting what the program is supposed to do. String length is supposed to return an unsigned integer. Okay, so we'll just say it is supposed to return an unsigned int. And you pass a parameter that is a const char star, and P1, which is a pointer. And the way it works is you do need a local variable because we need to track how many bytes we have seen up to this point that are non-null. So you do need a local variable, which is also unsigned, and we'll call it count here. And we initialize count to 0 because we need to start counting from 0. And then the loop itself is actually very easy, okay? Because we just say that if P1 is pointing to something that is not null, then go ahead and do the following two things. I'm not using auto increment because that's combining dereferencing and auto increment can be a little bit confusing, even though it's not really that confusing. So I'm not going to do that in this particular program. So we increment P1, and then we also increment count, which is just adding count by 1. And by the time we exit the loop, count is what we are supposed to be returning.
You didn't actually increment count.
Oh, okay, we just say count. The C compiler would actually be okay with that. If you turn on optimization and warn all, it might give you a warning as I can say that this expression doesn't do anything. Okay, so are there any questions about the C code itself? Okay, no questions? All right. Because based on what you have learned in cisp310, this program should be readable. Okay, yep, go ahead.
Also, what assumptions can we make about the registers and what's already?
Okay, so we'll write that down here. Okay, so we can assume register B is P1, return value is going to be in register A. Okay? And then the rest is up to you. Okay, which register do you want to use for the count purposes? It's up to you. Okay, so it's all about conventions and which way works better for you. Okay. All right, so this document is the starting point. So the next step is to look into this code and say, okay, we are not implementing subroutines just yet. So I'm just going to extract the actual code here and say, register A is getting the count value here, but there's no need to actually do that because you just need to dedicate a register for count, which is register A in this case. So we still have 2 additional registers because we need some additional registers for all kinds of stuff like comparing what is dereferencing and adding. So a lot of stuff need a temporary register. Okay, are we doing okay so far with this? Just to make this a little bit easier, I'm going to change this register A to register C. C for counting. Okay, so that's easier because I usually use register A for all the little as a little scratch pad. Okay, all right. Okay, so let's go ahead and get it started. Yep.
Can we get like 5 minutes in the class to let everybody try it before we?
Before I start explaining.
Yeah.
Yep, we can do that. Sure.
Oh, what, write the program in C?
Or at least to think about it, just think about it. The C code is already done. The C code is done. So your job is to become the compiler first. Okay, compile this code into the quote-unquote assembly code. Okay, which is kind of like PC equals A, that sort of thing. That's the assembly code. And then from there, you have to convert it into actual opcode, which is the job of the assembler. Okay, so I'll go ahead and let you guys have a little bit of fun with this. And I don't really like to record, dead time, so I'm gonna stop the recorder. Well, let's see. Should I do it? I can just keep it going.
Yeah,
Google has enough space.
Answer about.
Just the processors will read 64 bits.
Okay, let me
Program.
just go back to the document so you guys can look at it.
If you got multiple cores, you got multiple threads. Yeah.
It'd be a challenge, but I have no files right in front of me,
So the first,
do that.
first thread takes
Mhm.
How many of the commands do you already implement for your tiny programs?
None. That wouldn't take me much time. Writing the parser to do with a ROM file and generator to generate a ROM file, that's the more complicated part. Because unlike your program, which can just generate, mine actually has to incorporate additional opcode into an existing file.
Yeah, but at least mine already gets
No, he's giving us a
address in the command for each one.
5-minute test
For what?
to see if we can convert that to.
To actual opcodes. Same
It's on the
place
screen.
under my processor folder. It's called string length. Just double checking. Yep.
Where is it? It's not in there. Where is?
Bruce Douglas. That's the guy who was teaching assembly language at Sac City.
Where did you put it? It's not
Yeah,
yours?
I can't find it either.
It should be under processors. It's a different file. So
Yeah,
go to the
to
same folder.
I go to microcode representation, go to the shared folder. Implementation too. Hit that, go to the shared folder.
Oh, okay.
Oh, I had to refresh the folder. That was why.
At least that's how I find it.
Yep.
Okay. Good level load. I'm kinda cheating looking at the notes in class, but.
It's not cheating.
You guys can bookmark
Those
it.
from class
If you
are
have your
allowed.
own laptop computer, you can just bookmark it.
Or if it's assigned to your Google account, then go to it. It'll always be shown under shared with me.
Okay. I think you have to use it at least once, then you will remember.
Yeah, that's when I went to shared with me processor. It's always gonna be there.
So he did the first part for us, got rid of the, okay.
There are no return statements. Oh, never mind.
Yeah, this is the alternative to this class.
I'm fine with this class.
I guess it really does not apply to people who are here in this lab. But for people who want to take this class, but from somebody other than me, this is the alternative.
How do you define
Is it
your
easier?
data before you begin? Data?
Yeah, we don't need to do that.
Well, how do you do the count part then?
the count part?
Outside count counting?
Just use a register as count.
Okay.
Yeah, just use one of the registers.
But for the return, does it matter?
For the return, we use register C.
Oh, it didn't.
So register C is count basically, which is also how you return the value. I chose to use a register C because C for count, that makes it a little bit
Yeah.
easier. Mm,
I don't think there's that many. Considering how
there are
big
multiple
that-
ways. I mean, there are always multiple ways to do it.
So you just try to fire it up in C, or you try to break it down into assembly?
They're all trying to break it down to opcode, like just like what we did in class. You can, if you don't feel like doing the whole thing, you can do a part of it, but it's still a useful,
I am looking at
process.
the notes. I had to similar notes here so I can like glance over.
Like, see how you use register A, I use register D for that. You can use whatever you want. There are multiple ways to kind of do it. A little tiny variation. So this is what I did. Is this the correct way to format it? Register A equals 0. Register B equals
Yep, we
1.
got a new one.
Yeah, pretty much. Native version. Says terminated, we go to G1 and return. Otherwise, B equals B plus B, which means they make B 0 right now.
Wait, why? Because B starts with the location array appointed by that you're showing.
B would.
So it's already initialized.
Oh. So that I do this right? Because I got A equals A plus D, and that keeps doing the counter. And then once I go to G1, C equals A. I initialize A to 0. I initialize register D to 1 for the counter. As a counter.
Return values and registers.
Yeah.
Well, I don't even need it.
You may not be able to keep the constants in the registers because we only have 4 registers and you need one for dereferencing.
So what I would do here
Yeah.
is
You
all you
return.
do is look at the
Sorry?
You only get a null.
You keep going, you keep incrementing until you see a null character.
So it just
So the C
count
already goes
basically
0.
just is count plus 1.
Yeah,
So
count
no,
gets
it doesn't.
count plus
So you
1
get
is inside the loop,
you get a
correct?
A, you get a 0, you don't-
Until you get a null character, right?
And then you
Yep.
don't have return elements.
Right.
You do need a G1, but you-
So it's a little bit easier than the one that we talked about in class because we are not comparing what pointers point to. Well, there's 1, but you're comparing to 0 in this case. Yep.
Is const ever implemented in hardware?
Yes, there are architectures that has const implemented in hardware. To load a 0 into something, there's a trick to do it. You can also subtract. You can always subtract the register from itself. So count equals to 0 is actually pretty easy to do. Putting a 0 into a register.
Register minus itself.
Yeah. And it's faster too because you don't need to go fetch the byte next to the opcode, which is a memory operation. So subtraction from a register itself is purely inside the processor. So other than the time to fetch the opcode, it has no extra memory access. So it's a fast operation.
Do compilers do that?
Yeah. Yeah, compilers would do that, but you have to enter the amount of clock cycles, combined with memory cycles, so that the optimizer can choose. Yep. Yep. There are various optimization techniques, and this kind of thing belongs to what we call Peephole Optimization. So you're basically just looking at what you want to do as a regular instruction, and then you replace it with quote unquote equivalent but faster instructions.
Oh, yeah.
Huh? No, not really. It's really just a search replace kind of thing. When you look at the assembly code, you go like, oh, I know this sequence of operations can be done faster using this alternative. So the code generator doesn't try to do any optimization. The code generator is really just structurally and not so intelligently crank out code based on the pattern, and then you. Yeah, so the optimization part is really just going through the output from the parser, or the first generation, and then you go like, oh, okay, these things, I can recognize this pattern. These 5 instructions can be done with these 3 instructions a lot faster. So that's called peephole optimization. It's context. It doesn't really look into the context of the entire program. It just looks at like a window of instructions and say, okay, I recognize this pattern. It's basically just recognition of patterns and replacement. But optimization these days get a lot harder because a lot of stuff is done inside the processor at runtime, at real time. So the processor can reschedule the execution of on its own to optimize its own internal pathway. So the number of clocks it takes for one instruction to execute is no longer quote unquote predictable.
How does it do load balancing? How does it do load balancing like this?
Load balancing?
Using hardware?
Using hardware. If you look into the documentation of the i5, the i7 processors, and even the i3, it has got some internal scheduler.
How does that work?
It queues up, what needs to be done. So it has a small window of look ahead of, okay, I can see that I'm doing this, and then this, and then that. Okay. So if you have a slight look ahead, then you can say, okay, I know this will involve this ALU, that will involve that ALU, and this needs the result of that, and so on and so forth. So internal to the processor, it can now start to do some optimization to basically reduce the amount of time it takes to execute those instructions. Yeah, because you can't have 4 instructions. Let's say you have 4 instructions. The first 2 can be done in parallel because they have nothing to do with each other. The third one relies on the first one, and the fourth one relies on the second one. Okay, so you have a small window of 4 instructions. So if you execute instructions just one by one, okay, then you won't be utilizing all the ALUs in parallel, assuming that all of those operations are register operations and none of those require memory access.
That's how you.
So what the processor would do is it would look into the actual queue of instructions to be executed in the next few clocks and go like, I don't know, in terms of transistors.
Yeah.
I don't know exactly, but I know the Intel processor does that.
That sounds like a lot of overheads to check everything in advance.
I don't know how they do it, but it does. It is implemented in the Intel processors.
Is it less power efficient, or is it just more performance oriented?
I think it's more performance oriented compared to saving energy. So when you look at the amount of energy it takes to do a particular calculation, this is not going to improve it.
This
Not.
Okay.
Not.
That's close. Yeah. But then you have to.
Why'd you do
You need the jumps to and also the conditional values. So
Well, this is what I've got to do before I use the
area. So if we're at the end, it'll be 0 minus.
So the opposite approach to what I just described is the total risk way to do it. So you have tiny little processors that has no optimization other than pipeline optimization. Pipeline optimization is easier to do. It's basically just saying, okay, yep, go ahead.
I'm gonna check the program to see if I before I actually convert to the actual opcode.
Okay. So we have okay. So G1 is the beginning. DCA. So the AC was right, okay, that's example right. Yes.
I don't know. We'll find out.
It doesn't have to go back to the A. Yep, that's it. Yep.
Right, that's what it's
Mr. Joe was saying, you know,
So,
I had to look at
you're
it.
flattening the code.
Yep, you flatten the code first, so that you get rid of the while and you replace it with the condition that goes in.
So,
Yeah.
Basically, ask the question, how do I get out of the That's the condition that you need for the condition of.
Like I was doing with actual bike codes.
so you get out of the loop and this is
Oh, we don't just assume that he wants to.
Well, when do we stay in the loop? We stay in the loop when whatever the order points to is not no. So we get out when it is no, which is basically if it is
Like Shane
no.
said, I think so. Yeah, I understand.
So, focus on everything else later. So, let's see, I used to see it when you right? So, this is what I did.
When I'm around smart, I still have it. When I'm around the rest of the people I know, I feel like a smart.
I'm still trying to figure out how this word works. For the while, did you have
I don't have any.
like, okay, so I told you while it's checking this, right? It's checking whatever data is within this memory address, right? But I'm checking the data.
You're not changing the data, you're changing the address. So we need to start as the reference. So checking what is in that radiation.
Yeah.
Yeah, whatever number is there.
Yeah. So whatever action is whatever
But we don't need to create secret CRV.
And then here you're going to the next address, you're going to the next character.
How long is it?
Okay, so in the memory address, each location signifies one character.
Yeah.
Oh, okay. And then, no, that makes sense. Okay, and then how do you know when to stop? Oh, it knows when to stop when that becomes null.
Correct. When you do it,
When
checking at zero.
it checks and it's nothing there. That's how it
Or
knows.
if it's equal to zero. Like remember the tricking in class, checking the other equal to zero. That's what you gotta do.
Okay. I'm like thinking, how does this thing know when to stop? But it's going, okay, first element, there's some data there. Next element, there's some data there. Next element, there's data there. Next element, there's data there. Then, boom, it's a null. Oh, there's nothing in here. It's zero. Okay, I stop now. Okay, so then I'm gonna say, if this not equals, basically,
So that actually
How does this?
happens when you go.
I understand we don't
not
care
equal
about
zero. I know it's not
because
equal
we
zero.
don't
I
basically
say
go to this and not see what instead. Okay, well, like, okay, so we have if star B is 1 to 0, is 4 here, then the thing is I'm trying to understand, like, we don't care about register A or register.
Can I say this?
We don't care about B and C.
Yeah, but
Can I say this right here? No.
Yeah, you need A for a jump.
Yeah, exercise.
Yeah, well,
Okay.
okay, so PC starts off with 0, but we need.
That's what you're checking for. Now you gotta like
Oh, H your counter.
I would do like, I would subtract them from myself and then set the Z flag. If the Z flag, I would subtract them from myself and then set the Z flag.
That's when the zero plus is 0.
Yeah, I just
Zero
that.
minus zero equals 0.
This is how I did it instead of watching me.
Right?
What I did was.
So you're gonna need a load zero is a register somewhere.
Yeah, we're assuming the starting point is
So C starts as a random account. And A is replaced with your account. And every time it increments is 1, I would just add it to B.
I think one of the things that's getting confused
So what I did is I would just
between
this.
what happens
What was C, right?
at the assembly level versus what happens at the higher level.
Yeah, just flat.
So I checked if Z is 0, and we want to skip this guy to the end, right? D is 1, yeah, so we're adding the count C is 0, and you're adding C with D. So
That's
that's
the
C, right? So it's A.
Oh, yeah, just in this case, you will be.
So that would be,
one less.
That's the point. The whole point is that you used to keep going through the string.
So what do I gotta do?
So why not just save one register?
Okay.
Well, I guess you could. You could.
7.
Instead just at the end.
Minus B.
So 1 1.
But yeah, that kind of makes sense. Replace it with A, just like you did in the This is last step.
Okay, one more question. I'm looking at this. See, we incremented this one, right? It's another register.
It's post.
Post.
I'm talking about up here, A, why are you saying A to 0 on that?
I'm trying to do it, it's just like, it's like really hard to randomly take just pieces of what's happening. Like here, and then shifting this around and moving it here.
What I would, what helped me,
This is after you use this, you will use
See my P1s?
your
Read
P1.
register P.
Okay, are you ready?
I think I have the answer.
But I commented it out
I just
so
wanna
that
check.
I can.
Okay. So I'll just go ahead and, are you guys ready? Does anyone want a little bit more time or
Some more time.
A little bit.
a little bit? Okay.
I'm like
5 minutes.
close, and I don't want to like, I don't want the answer.
So I think one of the issues I'm having is like kind of conflating the assembler step with the compiler step.
Okay.
But
Yeah. So then.
so
Okay, so one thing you can do is to look at the document of the string compare, and then see how I go from one step.
Yeah, so far you're good. I just did simplify it some more. Got rid of the negation.
yeah.
How to implement this.
Are we gonna use a register to
The only thing we can
put a
do-
number 1 in a register?
Yeah, you have to, yeah.
Really? Okay.
Because the only thing we can do is to add two registers.
So you have to set one register to 1 and 1 to 0, so that you can compare to the 0 and then ignore it by 1, right?
Right, so there's one scratch pad or two scratch pad registers that we have to track all the time, because we have to do all the stuff to make use of those registers.
D, A, and D, because you have D
Yes.
as your P1 and C as the kernels.
Right.
And then A and D would have to be 0 and 1, 1, 1, 0.
P3.
Is one to compare to 0 and then the
Wow, okay,
Yeah.
so,
But you can reuse the same register, right?
Is that in
so I basically designate by 1 register?
No, I wouldn't do that. I would just say whenever you need it, then you can just,
How do you make that
to the scratch pad register. Whenever you
You've already
need
gotten
it,
to
put
it.
the
My
zero.
idea is basically
So
program
it would be an extra step.
the entirety of the processor in C.
Yeah, but you only got 4 registers.
I would
So
do
you
the add.
cannot afford to say, oh, this register is stored constant, this register every store.
Rewrite it.
So you have to have it random, you have to have a
Right.
location.
Well, you can do that to
Specific location that's
Well,
yours.
no.
And the specific
Not only
spot that
assembler,
it's
but
in.
assembler, compiler, and
So that's,
runtime.
yeah, we have
Yes.
to take it
So
from
then
That's
memory.
right after the
emulator where
output
you
of
can
the
put in
LTI
assembly language commands
Well,
to tell it to
that's
do a
fine.
process of things. Like I wanted
So
to do a string
basically,
compare and a
it would
string
be
copy.
more optimized.
And I wanted to
keep those
store it as
registers
files.
just the constants.
And
But-
then you
can, but
And so what you'll have it do is you'll just have it run exactly like the
We have
processor
64
would.
registers.
And it would
Sure.
take it to a file, take it in,
This is
do
the
your
only program
necessary
the processor will ever run.
information, and then spit it back into a new file.
But you would use a
Basically, you will give it the raw,
Well, I guess this is one of those
with the RAM, and then give you a new RAM, like what does the RAM when you're done?
Exactly, you've already
Well, this is a
programmed your
very
ROM, so you
minimal
load your ROM in.
processor.
give it commands in assembly, which are transferred into bitwise operations that would be put into the RAM and log assembly.
Like have the assembler converted to these actual bytes, and then just have it.
Exactly. Or what you do is you store these bytes in a file. You name whatever the name is that you want. Like this would be string compare, strcmp. So you open up your little program, you tell it which ROM you want, and then you say string compare file name, and it would compare two strings from two files and spit out the answer to 30 files.
But I'm using a minimalist design here. That's why it doesn't have that. Okay. Are we ready?
I'm ready. I might be stuck, so.
Okay, so let's go ahead and do this. Okay. All right, so let's go ahead and do this. Okay. All right, so register C is the one that is that's a counter. So if you want to clear register C, you can do the same thing that we usually do, which is C equals to PC plus star PC plus plus. But there's another way to do it that's faster.
Oh yeah.
You can do this, right? C equals C minus C. Okay. Now it is a lot faster because it doesn't need any extra memory access. This is all between the registers and the ALU. It's done really fast. Okay. So C minus equals C is one thing you can do to just clear the register C. So I'm just going to comment the instruction that I'm implementing or that I have already implemented. So the next one is to take care of the while. Okay, now remember we have to flatten the program first, which means if it says while blah blah blah, we have to convert the while into a if go to and then define a label accordingly. So the way to do this is we are saying if not star P1 go to label, we'll call this G1, and then G1 is right after the loop, so G1 is defined here. Okay, are there any questions about how to get rid of the while? Now, we are not quite done with getting rid of the while because we are just specifying the code to get out of the loop, but we still need the code to go back to the beginning of the loop. So we still need one extra go to in the body of the loop itself, and say go to G0, and then define G0 to be at the very beginning over here. Are there any questions? Because in this particular step, I just took out the count equal to 0 because that's the easiest one. And then I converted the loop to only make use of a conditional branch and also unconditional go to. Is that part okay?
That's why.
Is that okay? All right. Okay. So with this change, there's no need to use these braces anymore, because these braces are only required when we have a structured program. This program is no longer structured as far as using control structure is concerned, so that's why we don't need the curly braces anymore. And then on top of that, I still want to keep the indentation because I still want to maintain the structure of the code conceptually, even though I'm not using curly braces or structure control structures anymore. Is that okay so far? Okay. So now we take this code, and then we say, okay, find out how to do any further implementation. So this is the first thing I want to implement, okay? And I think your P1 is register B, right? Okay, so the way to do this is to say, okay, let's find out what is in register B, and we'll put it in a register, let's say A. Okay, so we say A equals to whatever is in B. We need to compare that to 0, okay? Now you can say the count was 0, but count is a counter. We cannot rely on count being 0 all the time. So you don't really have a choice here but to turn D into 0. Now once again, you can do something like this to basically just to make D into a 0. So it would basically be doing the same thing as D equals star PC plus plus and put a 0 after that opcode. But this is a faster way to do it, because when you subtract D from D, what do you get? 0. You store it back into 0, so you store that back into register D, so as a result, D becomes 0. Okay. Okay. But now we need to use the condition of, we need to compare, okay? So compare is really just a subtraction without storing the result. So in this case, it's A minus D because A contains the byte pointed to by register B, and then D is just 0. So we do a compare with 0 in this case. As a result of compare with 0, the Z flag will be set as long as A is 0 as well. The Z flag is going to be set, which is perfect for us because we want to get out when P1 points to a null character. So that's why this is a perfect time to say PC equals. Oh, I forgot one thing. Okay, let's not forget to load the destination address into A first. So in this case, the destination address is G1, but the instruction that we use to put G1 into A is A equals star PC++. But I do have to comment that we are going to use G1 as the number to put into A. So the next instruction can now be PC equals A if and only if Z is 1. Okay? Are there any questions about this code at this point? Yep.
Why'd you do C minus equals C? I mean, I see you can get 0 that way, but can you also set it with C equals program time?
Star PC++?
Yeah.
Yeah, you can do that.
Okay.
But this is a little bit faster.
Yes, it is.
Because you don't need to access memory in this case. Okay, so moving on. Okay, so moving on, we got that one done. So now we can implement plus P1. Plus P1 needs basically it's just adding 1 to register B. So we need to put the 1 into A register first. So we'll do a. We can just reuse A. So A is star PC++. In this case, we just want a 1. We just want to copy the bit pattern of 1 into register A. And then we say B plus equals A. And then with the next one, because we already have A being 1, so we don't need to reload it with a 1. Then yep, this is just C plus equals A. And then we have this unconditional branch here, a goto, which requires you to do a equals star PC++, and this time we want a label G0 in register A, and then we have an unconditional branch which is PC equals A. So that will branch it back to the beginning. And I think this is the entire program because by the time we get to G1, we can halt. The program is done at that point. So at G1, we just say halt. Okay, so that's the entire program. Any questions about this entire program?
So we have to load the registers from the RAM, and then use the registers.
Yep. So the next step, is the really tedious step, which I really don't think we have to do it too many times, is to convert this form into the actual opcode, the actual zeros and ones. You guys want to do that, or?
I already did. I'm good.
You're good?
I know listening over here.
Okay. But that's it. This is the whole process of converting a program or pseudocode, in this case written in C and C++, into assembly code, and then from here you have the option to convert it into opcode as well, the actual binary opcode.
In our exam, are we going to be converting to opcode too?
I haven't decided yet.
So we should.
Will we know on Tuesday?
Yeah, we'll know on Tuesday. I will give you guys a practice exam, which is unlike the practice exam from last year because this is not how I taught the class last year.
Last year's was more difficult.
Different. It's hard to say whether it's more difficult or not. Well, okay, there's a reason why I'm teaching the class like this, why I changed the way I teach this class. Because before, okay, let me show you how other professors teach this class. Okay, not to say whether it is right or wrong. Okay. So this is the curriculum of Sac City for exactly the same class, and you can see they talk about decimal, binary, hexadecimal, signed and unsigned. Okay, we got that right. And then they jump into PC architecture, and look at how much time they allocate to PC architecture. 3 hours. And how much time did we spend on processor architecture?
6 weeks.
3 weeks? Are you kidding me? Everything from the beginning of the semester up to now is PC architecture. Okay? So we spent, easily about 30 hours on PC architecture. Okay? But when you look at the actual topic, okay, PC architecture, segment, offset addressing, general registers, flags, those are not only specific to the x86 architecture, they're only specific to the early day PC architecture, the 286 processor. Well, the 8086 has that too. But some of those do not even apply to the modern processors anymore. Past the i386, we don't really use segmentation or segments, the segment registers or offset addressing anymore. So this stuff is tracing its way all the way back to the x86 processor, not any modern architecture. But the problem that I have with something like this is when they talk about these instructions, when they talk about arithmetic instructions like compare and jump, stuff like this, and how to allow changes in registers, stack, and data segment, those instructions will basically make no sense whatsoever unless you know what is going on inside the processor. Because the first question or the first confusion, when I taught a class like this before, the first confusion was, what is a register versus what is memory? Okay, and what does jump actually do? Okay, well, a jump is really just continuing execution at another location, but how is it done? Well, because the program counter was never exposed, people don't understand that we are just changing the program counter so that we control which instruction is the next instruction that we want to execute.
And without seeing it, seeing it and playing with it, really deepens the understanding of I can see how you call it simple, and it can be perceived as very simple. When you really see what's really happening, it actually is simple in its own way. It's just hard to convey that without showing someone that.
Right.
I can see why you decided to change it, to change the order and what you taught.
Right, because when you look at this slide here, when do they talk about addressing modes? Okay, they talk about addressing modes all the way to the end of the whole semester. Okay, so they talk about these register addressing modes: register, direct, immediate, register, indirect, indexed, based, and base indexed. Okay, these are all specific to the Intel processor. Okay, and some of these are very cisp features, which means they are really just there to help things to help to simplify from the perspective of the programmer, but it complicates silicon. It complicates the actual design of the processor. Okay, so when you look at this topic, just look at the addressing modes topic. We have done register. Every single time an instruction changes a register, it is using what we call the register addressing mode. Done. Okay. We are done with immediate as well, because every time you use the LDI instruction or A, B, C, or D equals to star PC++, that's immediate. Okay. Whatever is next to the opcode specifies the actual bit pattern that you use to update a register. That is immediate. We also talked about register indirect, which is this one here. Every time you see the asterisk symbol, asterisk B, asterisk C, and so on, that is indirect. Then what about all of the other ones? They can all be emulated using these three. And that's why we don't talk about those when we talk about the actual simple processor. Are we doing okay so far with this? Okay, because I do want to correlate what I teach with the actual curriculum. Is that okay? So I chose to teach this class in a way where we actually explore the actual, what is inside the processor first, because when I explain it that way, and you go okay, I have no idea why this program works, because we can actually put in the program into RAM to execute the string compare. Okay, and once I have the full ROM specified, we can actually do that. Okay, and then you can actually see, it does return the correct value or not, right? But the nice thing about that is, if you ever have any question about, I don't understand how this works, well, guess what? You just need to look into the processor architecture, single step, and then probe the wires and find out exactly what is going on. The only thing that is kind of beyond my explanation is how multiplexers work, how demultiplexers work, how decoders work. But those are all explained inside logic sim anyway. Okay, so we boil everything down to, basically just gate operations. So whenever you look at a high-level program, you go like, oh, I don't understand how this instruction works. Why are we continuing execution back in the earlier place? Just execute it slow, okay? Figure out that, okay, we are changing register A to be a particular value, and then that value in the end ends up in the program counter PC. And then when you look up the processor architecture, you can see how the program counter hooks up to the address bus, but you have to kind of switch a few things first so that it controls the address bus. But that's the reason why I am teaching the class the way I'm teaching in this particular semester. It's from the ground up, from low level up to high level.
In your previous classes, were you finding that you had to explain the hardware stuff more in depth just by default?
It's just that people have more confusion when I talk about the addressing modes, and people still have confusions at the very end of the semester. So I felt that I was not actually teaching the concept, well, because people don't understand what is going on behind the scenes. As opposed to in this class, you guys can track down everything.
I completely feel like I understand registers.
Right. Now, at some point,
I feel like I can explain it to a kid.
Yeah, but that's good.
So
But in this class, the idea is, even though remember how we started off this class? We started off with transistors, right? And we kept on transistors for a little bit, okay, until we get to NAND 2 gates, and then we say, okay, with a NAND 2 gate, we can do everything else. But after that, I don't really mention transistors anymore, okay? So once we get to the basic logic gates, then we pile up bigger things, okay? The infamous adder and the subtractor, okay? We talk about flip-flops, we talk about latches and stuff like that. But once we understand the mechanism of those things, I don't go back and re-explain everything from the transistor level up, because I'm assuming that we can just go down one level and drop it another level, drop it another level, and then we get that. So it is the same thing here. So after a while, we are not going to go back and look at the processor schematic anymore, assuming that we understand how it works. Okay, there's no need to memorize that thing. Okay, you just have to understand how the various components are connected and how the processor as a whole operates. Is that okay? So this is where we stand right now. Is we are done pretty much with the toy processor, and I'm using the toy processor to convert high-level C code into quote-unquote assembly code, and sometimes we go even one step further into the actual opcode. Now the conversion into the opcode is necessary if I want to run the programs using the toy processor, which I feel is necessary because I personally like to know whether the programs work or not. Okay, I don't want to just kind of crank out the code and go like, yeah, it should work. Okay, because that's a famous last word. Should work. No. So that's kind of the reason why the way I explain things. A lot of these topics, for instance, near, far, public, macros, and stuff like that, those are also specific to the Intel processor, okay, which I feel is not really that helpful because I want to teach the concept and not so much features that are specific to certain processors. The toy processor is not a commercial processor. You will never find it actually implemented. But it does illustrate all the basic concepts that we need to understand in this class. And you can play with it. I mean, you can just download the ROM file, you can download the processor architecture, and you say, well, Tag, I really don't like the fact that we cannot just add 1 to a register. Change it. Okay? Change the processor architecture so that you can increment by 1. What would that involve? What do you think? Well, there are several ways to do it.
Well, adding.
Go ahead. Okay. You can use an adder. You can basically just there are 2 ways to do it. One is to have the data path to feed into the second operand of the ALU. Okay, but when you do something like that, you will also need an additional mux because now the input into the second operand of the ALU can be coming from a register or from the data bus directly. So you will need at least one more select bit out of the ROM. Okay, now we'll need 27 bits instead of 26. to control that one little switch and say, do we want to specify the second input from data or from from a register? So that's one way to do it. You can also have a specialized increment operator. Okay, to just add one. There are many ways to do it. It's just a matter of figuring out what you think is the easiest to do it. But regardless of what you do, you probably have to end up using an additional line from the ROM. Yep.
I remember you said you're on the committee for suggesting changes and stuff to all this computer science stuff.
Yeah.
I suggest this should be a 2-semester class. Next semester we build a real CPU, 8 bits in an FPGA or something. So I'd love to have like an actual.
I would love to do that. Okay, I would love to teach embedded system programming, real-time programming, and that sort of thing. The problem is we are limited by how many units we can offer in the transfer degree, and we are already over. How many units is one calculus class? 5. Yep, that's the reason. Okay. So the CID or the course ID organization, who's trying to unify the courses, the course descriptions, and the curriculum and stuff like that across the entire state of California, has placed an upper limit of the transfer degree of computer science can only be up to I think as far as I can remember is 60 units. When you combine all the units that we offer here is already way over 60. And part of the reason is because calculus classes in a UC or CSU are 3-unit classes. Your calculus 1 is a 3-unit class, but here it is a 5-unit class. So those extra units is chewing up the 60-unit limit that the state has imposed on a transfer degree.
So if you have too many units, you can't transfer.
You can transfer, just they won't count all those units to your graduation requirements. They'll still count the requirements for your
But you'll lose units.
classes. You lose those extra units,
Well,
yeah, so you're gonna have to fill up your 120
You
at
start
college.
losing your priority in registration. You start losing your ability to get financial aid.
IRC, but when you transfer, it's
Then we'll just like at the end we have to start padding a bunch of like
Yep.
Bullshit classes just to
Yeah.
get your
Fluff,
readers back up.
fluff.
well, they should raise the limit. We're
Bird courses.
we're not liberal arts majors. we're
Just
computer
flat
scientists.
Well, but that's something that they have to adjust in the statewide organization and not just at ARC. So that's the reason why I thought about breaking this class into two. The first class just talked about all the stuff that we talked about earlier, the gates, the transistors and stuff like that, and then the second class would actually focus on programming and in assembly and stuff like that. But that is not actually feasible, unfortunately. And I also got resistance from some other professors from a different college who says, Tech, you cannot teach, logic. Like in terms of logic gates and flip-flops and stuff like that. I go like, why? Because you're computer science. Okay, then who should be teaching these topics? Electrical engineers like myself. I go like, well, if anyone can scream and say you cannot teach, but only we can do it, those will be the math professors. Because logic gates, and or Boolean logic, Boolean algebra, it's math. Sorry?
Philosophy professors.
Yeah, it's almost
Sorry?
The philosophy professors are one up on math.
Yeah, or philosophy processors. Philosophy processors. Professors. Okay.
Is this bullshit?
To profess in something is to process that, okay, So I got resistance, I got pushback, from people, like that, who are basically saying, there's a line on the turf, this is yours and this is mine. Do not step over mine.
Well, then
What if
state
it
of
was like,
California
what if it was a
came and
class
said,
that was offered as like an elective course?
Sorry.
What if it was a class that was offered like as an elective?
Elective classes never get a go. Okay, just look at the number of people who show up in the lab. Okay, so I tried it many years ago. I actually started a robotics programming class. That I really seriously wanted to teach people how to do motion control, how to control stepper motors,
I would take it.
and stuff like that.
I would take it in a heartbeat.
The course went through the curriculum process, but because I cannot link it to a class that we can transfer to at a 4-year university, I cannot put it into the transfer degree.
That's
And if
fine.
something is not in a transfer degree, you can offer that. It's just an optional
People
class,
don't know it.
but nobody takes it.
Well, they're dumb. They don't
Well,
know.
people want to get a degree as soon as possible and get out of here and go into a four-year university.
That is true.
Like I'm taking Java, and I already took 400. I don't have to take Java, but I'm taking it because I want.
But there are not
the
enough
information.
people. You need 22 people in a class in order for it to go. And that's really, really hard to fill. 22 people in a class that is not required in a degree is really hard to fill.
Well, that's why we gotta advertise and say, hey guys, we're the only junior college offering this stuff. Come and take it instead of paying 12,000 at UC.
We try to do it in the career club, but in a career club, no one's in the career club. Like it's probably me, Mickey, like 2 other people.
Well,
that
it's
show up
not.
in there even
but,
remotely.
okay, but this year, Mickey is not really doing a whole lot to promote the club or to actually do something, that would attract people. So that's partially why the attendance of the club is kind of low this semester. So who's going to be president next year of the computer science club?
I would do it if I had the time to dedicate to it.
It is actually a good experience. If you want to kind of test your leadership skills and whatnot, that's actually a good opportunity.
Believe me, I would do it. I would do it in a heartbeat.
I would do it
I just,
only if you have FPGAs.
I just don't have the
So,
time.
so getting back to this, I think I'm not going to name the person, but somebody said, that these class, the way I teach this class is way too hard, and some people, would drop this class and take it, over at Sac City. It doesn't hurt my feelings at all. Okay, so if anyone here or someone who's watching the video says, oh, okay, so there's an easier way to fulfill this requirement, yes, go ahead, take this class over at Sac City or Consumers. Huh?
To all YouTube
Oh yeah,
viewers. I
to
know-
you all.
I think the class, I think the course
Right?
is difficult, honestly, like I think it's difficult, but
They only had it here.
I wouldn't want.
they only had it
I
here?
wouldn't want
Yeah,
the
that's why I
easy
had
ass
it
class
here.
where
Okay.
Just mention it, I'm not gonna finish that.
like,
Let me see if it's offered this
Without
semester
fail,
in
Yeah,
West.
I think they added it on
Class,
later.
I had them.
When
Oh,
I was
okay.
signing up in April.
Yes. And then
Every
they're gonna have that.
have it, they only had it for you.
I've never had a class that's done that. I might have a class where like every once in a while, like, oh wow, that's really cool, something I didn't even think of at all. This is like every day is like, wow.
Yeah. Well,
Wow,
now
I
I
didn't
don't
even know.
necessarily
Wow.
take pride in anything, but I can tell you that people who go to Sac State or even Davis, they've come back and say they feel well prepared as a whole by classes that we offer here at AR. So I feel I feel comfortable because of that because one thing that people worry is okay when I transfer to a 4-year university, will I be able to catch up with students over there? Okay, I think it's a valid concern in some cases, but in my case, I really like to try my best so that my students would not feel that they're not connecting at a 4-year university.
That's why I like.
Do you teach like an app development class or something?
Like mobile?
I don't know, but like I was going through your videos and some problems, and one of them you pull up like a simulated cell phone, and you were like doing something on it.
Yeah, I teach mobile app programming, CISP 362, and next semester 363 in Java. 363 is in Java, 362 is in App Inventor, which
So
is
you
a
know Java good.
pretty easy thing.
Probably tell me what's wrong with my program.
That's paid tutoring.
I'll give you $1.
Okay, so they do have a different person teaching assembly programming now. It is Parlin. It's doesn't sound like
that's a
somebody
terrible time.
who I recognize.
Anyway.
This is also done in a hybrid fashion. So you can see the lecture is fully face-to-face, but the lab portion is quote-unquote online, which basically means you're on your own. But I use the lab time a lot to do lectures too. Just do demonstrations and explain concepts, which I think is really good.
It's very
because
helpful.
in previous semesters, I run out of time every semester to talk about enough topics because I only use the lab time for people to do the homework assignment, but I never really use it for instruction purposes. So this, starting from like 2 semesters ago, I started to use the lab time as well. Not every single one, but like today,
When it
I use
bleeds
it for
over.
instruction purposes. So so that's the kind of difference. Yep, go ahead.
It's kind of unrelated, but were the prerequisites like different a long time ago? Because like, why is 310 a lower value than like 360?
Well, it is 301, but 360 implies, CISP 300 or 301 already. Sac City has a 301 instead of a 300 because the way they describe the class is different. So in this case, I think because the way they don't want to teach the class the same way that we do in here in the other two colleges, so they decide to use a different number to classify that class, which causes all kinds of problems. So when people try to transfer from Sac City to ARC, they would not have taken CISP 300 because they would have taken CISP 301. But there's no equivalence established because 301 is not even offered here, so we don't have an equivalent listing of 301. So it just causes all kinds of problems. I'm just curious, does CRC offer this class?
I have a friend at Sac State. They don't teach any of the hardware side or assembly.
Okay, now this is also kind of interesting because they only use the lab portion that is face to face. The lecture portion is completely online, which basically translates to this is the section. Read chapter 5 over the next week.
That's how Antos.
I turned my.
And I cannot do that, because
It's difficult.
Because nobody reads it.
To be fair, I really like the way you do 310 and 440 because I feel like when I'm going to transfer, I'm not going to be behind. Because many people complain, what's all this stuff? I'm coming to college, it's like brand new terms I never heard before. But I feel this is like stuff I'm going to be learning at Berkeley or Davis, wherever I transfer.
well, I still miss certain things in 440 because I just ran out of time. I just flat out ran out of time.
Did you have a lab for that?
No, 440 has no labs. Okay, but this is the kind of the interesting part of CRC. When you look at the CRC classes, and we look into something like 400 or 430 or 440. Or 440, they actually have it fully online, fully face-to-face. But when you look at 400, it is completely online. Lecture, online, lab, online.
Are you think it was terrible?
Probably not.
I mean, C++ is already bad enough, and I have to do it online.
That's terrible.
Completely, 100% online. Now, some people can do that, okay? Some professors can teach effectively online. I am not one of those. I have ADD myself, so when I'm not in a classroom, at a particular time, at a particular place that I'm supposed to do a particular thing, I just wander off and do all kinds of stuff and get distracted. But in a classroom like this, I cannot get that distracted. Sometimes I do, but not terribly.
I can't learn that way. Like I'm terrible at like picking up information.
And then the other thing is you can get 90% of your score for your grade from your final grade before you take the final exam, which is the only component that is face to face. Okay, go ahead.
So, I was just curious if a way